which was an electric field of atoms and two equal charges. So during this class, some review is like we went over what a field is, and a field refers to a region of space in which a particular physical quantity is defined at every point. And we use like the example of like a football field, and each point in the field you defined it by like the yards in the football field. But specifically, what is an electric field? An electric field represents the force exerted by an electric charge at any point within a certain space. It describes how a charge would influence other charges around it. And then next, we went over like this practice problem. And the question was like in an ionized helium atom, the most probable distance between the nucleus and the electron is R equals 26.5 times 10 to the negative 12 meters. But it was asking what the electric field was due to the nucleus at the location of the electron. And he gave us this, which basically said like the distance is like so small that we can treat the two protons as a single charge as a 2e. And I have the steps for this question because he gave us the answers at the end, which was this right here. But the first step was to identify the charge of the nucleus, which we got. And then we had to apply Coulomb's law, where Coulomb's constant is like 8 times 8.9 times 10 to the 9. And basically with all that, we just had to substitute our known values and we get this answer right here. Sorry. But the next question we had was a little harder, and I remember it was pretty difficult when we were going over it in class, but it was when we had like two charges here, and we had to find the electric field and distance above the midpoint between the two charges. And sorry, but the steps were we had to first calculate the x and y components of the two charges, and since they were equal distance, the horizontal components canceled out, which is right here. And then, but the vertical components were given by this, but sorry. Oh, but since there was no horizontal component, we would only had to worry about the vertical. And when you simplify, basically get the answer down here. And that would just be the answer for both. Okay. But the conclusion is the magnitude of the electric field at the midpoint is approximately 2K, and this number right here. And we also went over what flux is. Flux quantifies how much of a certain quantity, such as electric field lines, fluid, or heat, passes through a surface. And the different types of flux were electric flux, magnetic flux, and fluid flux. And we also went over Gauss's law. Gauss's law is defined as the total flux out of the closed surface is equal to the total charge enclosed by the surface divided by the permittivity. And the electric flux through a surface is proportional to the total electric charge enclosed by that surface. It's also, this is how like it is defined like in an equation. But I think that was my whole presentation. Sorry.
Very good. Thank you. Um, is there anybody else? All right, very good, Dylan. Um, it's a good review. Also, can you please go to the chat and say I'm here, so I don't need to, at the end of the class, I can check the roster. So please just send a chat message saying that you're here. Okay. So if nobody else is going to present, so let me start with the presentation today. Um, see. So today we're going to cover electromagnetic waves. We kind of touch on that a little bit, you know, but today we're going to discuss how it is created, you know, how you generate an electromagnetic wave and how it propagates. So focus today is going to be on that. Um, so next class, we're going to have an in-person presentation of passion projects, 5 students. Um, Also, they are going to present their portfolio, lecture summary, and discuss a reflective question, the productive failure question. And you don't need to explain all of them, but if you can explain a couple of those that you think were more important for you in terms of learning and some that initiated with a misconception and then you learned um, the correct answer and you made a reflection about it. So those are the ones that I'm interested to have it discussed in class. Uh, I would encourage everyone to come to class because when students present their passion projects, we always learn something new. And when they present a lecture summary, that that is a review of what we covered, and is going to help you uh, on your part 2 of the final. There is a conceptual part of questions. You all have the 24 questions problems, part 1. Um, Try to complete those um, by the 21st. My suggestion is that you do a few of them every day, a couple of questions every day, so you focus and you do it the correct, give the correct solution. Okay. Is there any question about our schedule and
Prof- Professor, can I present on the 14th?
who's that? I don't know who's talking. Who said that?
No,
Oh, so you want to change? Where are you?
I'm
You are
not on this at all.
you. Oh, you're not on the schedule, are you?
No.
Um. Okay, so you want me to put here on the. How do you spell your name?
Kunal. Yeah. Thank
Okay.
you.
Is there anybody else that is not scheduled to present? So we have 2 students that have already presented. Okay. All right. So So this is the main question for today's lecture. By the end of this lecture, we'll be discussing all these things. What I'd like you to do now is to take some time and try to write as much as you can about your understanding of what is an electromagnetic wave, and also how does it differ from other types of waves. So you can give examples of other waves that you're familiar with, and then explain the electromagnetic wave. This is a very abstract uh, concept, you know, and I know it's difficult, but I just want you to try to be as descriptive as you can. The more you write about it, more ideas you have, the better, because when we go through, you know, uh, some of uh, evidence and during the lecture, you'll be able to, you know, make reflections on it. And explain the process of how the electromagnetic wave is generated, and describe how it propagates, okay? Um, Especially how it propagates in vacuum. And that would be extremely helpful if you try to illustrate, you know, your vision of how, you know, electromagnetic wave looks like. So I'll give you like 10 minutes to do that. This is extremely important. I'd like you today, a little bit after the end of the uh, class, to take a picture or scan it and send it, this response to me. Of course, you're going to post on your e-portfolio, but I'd like you to send it to my email. Is that okay?
Yeah, that's okay.
Go back. So what you're going to do, you're going to write down your ideas. After the lecture, you will have all the correct answers for this. And then you do the reflection. And please send that to me, all three pieces, all three parts of this question, um, by by email. Okay.
The length of the wave or the height of the wave, or is it something else?
No. So the question is, what is the main difference between the electromagnetic wave and other waves? But it's more, I know you guys thinking about frequency, or, you know, dimensions of the amplitude, or, but I think if you think about how the wave is propagated, you could see a main difference there. Does anybody has an idea, you know, what that would be? Because you know, this is one of the questions, right? And you probably wrote something. Everyone have written something, and so that's why I'm trying to hear from you. What is that you have written? You know, in terms of what is the main difference, you know, how they look different, you know, or the way they propagate, you know, is different. And what is that you came up with?
Excuse me, Professor, can I try?
Excuse me?
Excuse me, Professor, can I try?
Yes, go ahead.
The main difference between electromagnetic wave and the other wave is electromagnetic wave can travel without anything around them. My mean is it can travel in the vacuum. It doesn't need something like air or water like the other way. The
Yeah.
other difference is electromagnetic wave made of two parts, electric and magnetic, electric field and magnetic field, both.
Yes.
And mm, they are vary by size, like wavelength.
Mhm.
And they are like X-rays and light, radio wave. These are the kind of some kinds of electromagnetic field wave. Excuse me.
Yes. That's very good. Yeah. Yeah, that's true. You know, this is the main difference is that the first of all, the electromagnetic wave is formed by two parts. One is the electric wave and the other one is the magnetic wave, right? They go together, you know. And a way to understand this is it's how the electromagnetic wave is created, you know. This is, when you think about how the electromagnetic is generated, right? You kind of start understanding why um, the electric and the magnetic field goes together. You know, it's part of the wave. So how they propagate in vacuum is, is kind of a very abstract concept. It's very difficult to understand because in our world, all we see waves, they go through a medium, right? They need a medium. Sound, for instance, would not be transmitted if they were not for the air molecules, right, around us, right? We are immersed in this atmosphere that has molecules that when I say a word, create a wave by compression and that it transfers, right? It goes through that medium of molecules. The wave in the water, when the pebble falls in the middle of the lake, create a disturbance on the water, and actually, the water where the pebble falls is not moving, in the direction of the wave, you know, the water that, right there is going up and down. And this up and down is transferred, and to other molecules of water, and it propagates that way, So the energy is being propagated, but um, the actually molecule of the water is not moving in the same direction. It's just moving up and down. So this is very important to visualize that and understand that. Also, another thing is that, many descriptions of the electromagnetic waves on the textbooks, they show one dimension, right? But the electromagnetic actually goes in 3D, it's all over, the space is not going just in 3D. That's just a way to describe, when you look at the textbook, you see the electromagnetic wave formed by two, the electric field varying and also the magnetic field varying. Now, let's talk about how the electromagnetic wave is generated, because I think that's the key thing, it is generated by an electric charge. Okay, we learned already that a charge has an electric field, right? If the charge is not moving at all, it has an electric field. And that electric field, is spread out over the space. Now, when the electric field, when the charge is moving, let's say up and down, right? It's going to also to create a magnetic field. Okay, so the charge is not moving; it has only electric field. But the moment that the charge is being accelerated, up and down, it will generate the magnetic field. And you remember the experiment in our first day of class that we had the wire with a current on the wire. Ørsted experiment, right? We could visualize kind of, that there was a magnetic field being created around the conductor, right? So there we have electric charge being in motion or being accelerated inside the conductor, and that creates not only the electric field, right, but also the magnetic field that we can, show by bringing a compass close to the wire that, it lines up, and goes around the wire. We've seen that. So, but here, when we have this electric charge being moving, it's going to generate the electric field. Okay, so this is some explanation that you guys should visit here. So the first thing is it is connected to this oscillating electric and magnetic field because it is the effect of a charge being moving up and down, right? If the charge is not moving, then there is no electromagnetic wave. If a charge is not moving, there is only an electric field there. And the way, remember when the wire, the experiment, or Ørsted experiment, the magnetic field was perpendicular to the current, right? So that means if the charge is moving up and down, the magnetic field created is going to be perpendicular to that to the motion of the charge going up and down. It's going to be perpendicular, and that's it's how the electric field and the magnetic field are perpendicular. Okay. So another important thing is to understand that these waves are created by charged particles, like electrons. And also, a very important thing here is this understanding, I have highlighted there, that the electromagnetic wave is self-sustaining, what self-sustaining means, can anybody try to interpret this? Yeah, it is structured through the relationship between these two fields. And also does not need a physical medium, like we make it clear that electromagnetic wave can travel in vacuum. And an example of this is like stars. We can see stars from very far away, because of the light that travels in our direction. So, but it's still, I think, is kind of difficult to understand this idea that the electromagnetic wave is self-sustaining. Can anybody try to interpret what is your understanding when I say something like that? Why is self-sustaining? It is based on a concept that we already covered when we discussed that, a magnetic field can generate current in a moving conductor that goes through the magnetic field. That's one point to think about. The other one is that the magnetic field that is changing, varying, or oscillating, also, can generate a current on a wire, right? So the wire can be still not moving, but if the magnetic field is changing, it's going to create a current there.
Professor?
Or if the current is moving, right, is going to generate the magnetic field. So the electric field of this current that is moving is going to generate the magnetic field. Yeah, anybody want to say something?
Yes. Well, when I think of it and I think of like the electric field and you're saying how can we correlate that to an electromagnetic wave being self-sustaining? I think of it in a sense of like atoms are found in everything and atoms always kind of have a charge regardless of if they're in an environment or not. So that's how I correlate it because since there's atoms, the atoms will always self-sustain like the environment that they're in.
Mm-hmm. So the atoms, you're saying that the atoms are very everywhere, and because of that, you have self-sustaining. Is that your explanation, or?
Yeah, that's how I'm thinking about it because atoms always kind of have a charge to them. So,
Yes. And but what else is necessary? Yeah, the atoms. Atoms they are neutral, right? When you ionize an atom by maybe removing one electron, then it becomes charged, right? An electron is charged. Now, the idea that the electromagnetic wave is self-sustaining, what we have two things happening there. One is an electric field that is changing, and the other one is that the magnetic field is changing. So we learn that when we have a fixed magnetic field, like a permanent magnet, and we move a conductor across the magnetic field, a potential will be created on that conductor. And if we have a loop, right, closed loop, current will flow in that wire. And that is the principle of generators, right? Remember hydroelectric, you know, um, plant of, generator, it's based on the potential energy of water, um, falling from a height and being able to move a turbine, you know. So you converting this potential energy into some mechanical energy, motion, and the motion now needs to be converted into electric energy. And because, the turbine is connected to a rotor that has wires, the wires are moving. And if you provide a magnetic field, right? When the wire moves through the magnetic field, is going to create a current, and that's how we generate electricity in the hydroelectric. That's also how we generate electricity in a windmill. We see the wind is being used there now to propel a blade, and then that rotation, is connected to another, rotor with wires, and wires being, inside the magnetic field, and that's how it produces, electricity. So it is the fact that, once, one thing also to keep in mind is that, when I throw the pebble in the middle of the lake, right in the center of the lake, what happens to the pebble? Did you hear my question?
It sinks.
Yeah, the pebble sinks. This is very important to realize that the pebble sinks, but the wave that is being created keeps moving. So there is no need of the wave to have the pebble, besides it, to get moving, right? So the wave is being generated and now is moving, and it does not depend on the pebble anymore. So is an electric charge and the electromagnetic wave. Once for some reason, this electric charge is moving up and down, it's going to create this electromagnetic wave. And the electromagnetic wave is composed of two parts, the electric wave and the magnetic wave. And they go, together. And then they can go on vacuum, right? They don't need the electric charge anymore. They're being generated. It's a disturbance that has both. Now, because they are varying, because they're going up and down, they're changing, and there is a self-sustaining, because when a magnetic field varies, it generates an electric field, and where electric field varies generates a magnetic field. So it's kind of perpetual, you know, continuously generating each other. So that's why, you know, they can travel long distances, you know, and that's why they don't need the medium, because, you know, all they need is the electric and the magnetic field. Once created or generated, you know, they they don't need the medium like the water molecules or the air for the sound to keep being um uh, to keep moving. Is that okay?
Yeah, that's okay.
All right. So this is the title, and I have here a few videos that I found that are extremely interesting. I'm gonna show, let's see. I wanna start with this one. So this video I thought was extremely interesting. I'm not gonna show the video because this is like 28 minutes, but I do encourage uh, everyone to see it. You know, this is, you know, when they explain about, you know, wave behavior, and this is AT&T, and they get into, you know, a lot of detail. It's a historic kind of, you know, video, and that they do talk about, you know, semiconductors and things like that. So the link is there. So let's watch this other one here. This is also uh, a little bit of history, and I think it's important to understand because, you know, in 1956, they were starting, you know, discussing about applications for semiconductors and creating diodes. You know, that's when, you know, and I was born in 1957. So when I think about it, you know, it's 70 years that when they start looking into applications for that. And today we see what we have, you know, all this technology. But by the time of Maxwell, that was about 160 years, 180 years ago. And you see the struggle to get all these explanations of what is an electromagnetic wave. They still didn't know at the time. So today we are blessed that we have, you know, textbooks explaining all this to us. We have videos, we have all these things, but they had nothing, and they were still trying to come up. And watching this video, you're going to hopefully appreciate, you know, the effort and the dedication of these scientists.
student in college, just as you are now, I took a course in modern history. And one day during this course, the professor said, "And that brings us to the end of the 19th century." Well, I timidly raised my little hand, and I said, "Professor, sir," we were very respectful in those days, I said, "Sir, you spent 2 weeks teaching us about the theory of 19th century warfare, and you never said one word about the theories of James Clerk Maxwell. Now, the theory of 19th century warfare is a matter of no lasting significance, while what Maxwell did affects every single day of our lives. Don't you think that that's rather a bizarre distortion of what's important about history?" I guess maybe we weren't always so respectful after all. Well, to his credit, he was embarrassed by my question. He did know who Maxwell was, and he briefly explained to the class what he had done. But the point is that the history of science is the stepchild of the historical profession. Most historians just ignore it because they don't understand it. They're a little like the fellow who searched for his keys under the lamppost because that's where the light is, even though he had lost them somewhere else. Well, I'll tell you what I'm going to do. I'm not going to say a word about the history of theories of 19th century warfare, but I am going to tell you all about the beautiful theories of James Clerk Maxwell.
Elegant mathematical theories weren't the only things of beauty with which James Clerk Maxwell surrounded himself. There were his precious books, of course, and outside his well-appointed study, there were the rolling hills of Glenlair, the Maxwell family estate, 2 days' journey from Edinburgh. And every morning, even nearer to his heart, there was Catherine.
Good morning, James.
Oh, you're a funny lass. You brought me tea.
Yes, I brought you some tea.
They'd met in Aberdeen, at Marischal College, where he'd gone to teach in 1856. 2 years later, James wrote his Aunt Kay, "This comes to tell you that I am going to have a wife." He predicted that a new bride certainly won't stop mathematics. Characteristic of Maxwell's scientific predictions, this one proved accurate indeed. Of course, Maxwell wasn't the first to make accurate predictions about the deep mysteries of natural forces. 2 centuries earlier, Isaac Newton had written a book on the subject. But he'd had to express himself in terms of action at a distance. And that idea would come to be applied not only to gravity, but also to electricity and to magnetism. And then, in the 1830s, on the heels of the Frenchmen, Coulomb and Ampère, and especially on the trail of Hans Christian Ørsted, along came Michael Faraday. He'd been increasingly drawn toward electricity and magnetism, and by August of 1831, his path was reasonably clear. Picking up where Ørsted left off, Faraday confirmed that an electric current can produce a magnetic field. And then, going far beyond, Faraday demonstrated that a changing magnetic flux can create an electric current. And that a changing electric current in one circuit can induce current to flow in another. Thereafter, especially in light of similar discoveries by America's Joseph Henry, the principle of induction in the nature of electricity and magnetism was there for the scientific world to behold. And certainly within the Maxwell house, Faraday's experimental researches in electricity was considered the definitive text. But by the time he got hold of Faraday's work, Maxwell was ready to draw new conclusions, an ability which he developed early on. As a student at Cambridge, Maxwell's mathematics teacher observed, "It appears impossible for him to think incorrectly on physical subjects." Soon after that, as a graduate student, he wrote a paper that gave the scientific community reason to agree. It was called On Faraday's Lines of Force. And in preparation for that work, James Clerk Maxwell had done his homework. In the spring of 1846, Michael Faraday had penned a paper called Thoughts on Ray Vibrations. In that prophetic publication, he speculated that light is a type of vibration in the lines of force. The lines of force, he wrote, are known to connect particles and also masses of matter together. In other words, in Faraday's imagination, electric charges were linked together by lines of force in empty space. However, even though his idea was easy to see in the mind's eye, it introduced an intriguing scientific question. Would a vibrating charge set the lines of force into vibration? At this point, Faraday might have pictured each line behaving as if it were a linked row of mechanical oscillators. And in that case, he would have seen a disturbance propagate along the row, either as a longitudinal wave or as a transverse wave. But no matter how they might have taken shape in his mind, the significance of those vibrations was in the fact that Faraday had seen them. And somewhere between the lines of Michael Faraday's Thoughts on Ray Vibrations, James Clerk Maxwell would discover his electromagnetic theory of light. However, before he could read Faraday's handwriting on the wall to refine and polish it with his elegant mathematics, Maxwell needed to decipher a crucial clue. Within the forces of electricity and magnetism, he found a very significant speed. Any wave has a definite speed, depending on what makes it go. For example, in deep water, the speed of waves depends on the acceleration of gravity and the length of the wave. In air, the speed of sound depends on the air pressure as well as the density of the medium. And for linked oscillators, the speed is given by the spring constant, the mass, and the distance between oscillators. So it was time for Maxwell to get down to determining the speed of waves in Faraday's lines of force. From Maxwell's mathematical perspective, Faraday's lines were an expression of the 1/r² nature of the forces of gravity, of electricity, and of magnetism. At the same time, each of those has a specific constant. And in the right scientific hands, those facts got around to this. Since the fundamental forces of electricity and magnetism aren't independent, the electric constant, K sub E, and the magnetic constant, K sub M, should be related. But the question is, how? The ratio K sub E divided by K sub M has the units meters squared over seconds squared. In other words, the square of a speed. But what speed? Its square is 9 times 10 to the 16th meters squared per second squared. Divide the electric constant by the magnetic constant. And there it is, the speed of light.
Take your electrification by separating from...
It was an amazing discovery.
Now we can have a spot of tea.
After 50 years of the closest scientific scrutiny elsewhere, James Clerk Maxwell saw the light and found its speed in the forces of electricity and magnetism. But the fundamental forces weren't all that occupied Maxwell's mind. Around 1857, an academic prize was offered to anyone who could explain the solid nature of the rings of Saturn and their steady movement around the planet. Maxwell's answer was right on the mark. The only structure that could account for such stability, Maxwell wrote, was one made up of clusters of disconnected particles.
Those in which there is electrification.
Maxwell's essay not only won the Cambridge Prize, it won the praise of the scientific community at large. Sir George Airy, Britain's royal astronomer, called it a most remarkable application of mathematics. Perhaps because one good turn deserves another, Maxwell immediately set his sights on moving particles other than those of Saturn's rings.
Along a given path.
He developed a kinetic theory of gases in which gas molecules are small, elastic particles that collide with one another as they move about with various velocities. Maxwell believed all physics research should advance on, in his words, strict mechanical principles. That belief led not only to Maxwell's theory of gases, it led to his great accomplishments in electricity and magnetism. To pursue his research, the Maxwells moved to Kensington, London in 1860. For 5 years at King's College, he was productive in kinetic theory and electricity alike. And here at London's Royal Institution, Maxwell finally met Faraday. Faraday, remember, had seen electricity in mechanical terms, not merely as an idea in keeping with Newton's action at a distance, but as a thing of physical lines, a solid structure of force that radiated through space. Maxwell would state with great admiration that Faraday had seen a medium where the strict Newtonians saw nothing but distance. Perceptively, Maxwell added that Faraday sought the seed of the phenomena in real actions going on in the medium. Of course, as it would later be seen, the medium is the electromagnetic field, and that's where the action really is. But before Maxwell could get the message from the medium, he had to determine whether waves could travel through the electric and magnetic fields at the speed of light. If so, they would have to obey the 4 laws of electricity and magnetism.
The electric flux through any closed surface is equal to 4 pi K sub E times Q, or Q over epsilon naught, where Q is the total charge enclosed by the surface. and the magnetic flux through any closed surface is always equal to 0. These are Gauss's laws for electricity and magnetism. The circulation of magnetic field around any closed path is equal to mu naught times the electric current passing through that path. This is Ampere's law. The circulation of electric field around any closed path is equal to minus the rate of change of magnetic flux through that path. This is Faraday's law of electromagnetic induction.
So suppose that there can be a wave in the intensity of the electric field. This one's a transverse plane wave, and it travels, of course, at the speed of light. But consider the field at any one instant. Since it's up in one region and down in the next, it has a circulation about this path. According to Faraday's law, that means that there must be magnetic flux through that same path, and furthermore, that it must be changing in time. And that can only mean one thing. A magnetic wave must tag along with the electric wave everywhere it goes. But, and here's the crux of the problem, that in turn means at any instant there's a circulation of the magnetic field about this path. And according to Ampere's law, that can only be true if there's current flowing through it. But in empty space, there's no matter and no electric currents. So there's no way around the fact that according to the laws of electricity and magnetism in Maxwell's time, there could be absolutely no electromagnetic waves in space. The point was this. If the laws of physics stated that waves couldn't exist in empty space, could it have been that, as fundamental as they were, those laws were somehow incomplete?
Day 2.
Maxwell's task was to examine the fundamental laws of his era, and his triumph was to find the missing piece. And he did so by looking into a simple and altogether conventional apparatus, the capacitor. The magnetic circulation around any path depends on the electric current linked through the path. The only way to be sure that the current goes through the path is to imagine a membrane bounded by the path. Then the same current must pass through the membrane, no matter what shape the membrane takes. But that's no longer true if the current flows into a capacitor. Then, even though current is flowing, there may be none through the membrane. If so, what is the magnetic circulation equal to? Seeking an answer to that question, Maxwell took a page from Faraday's book. Changing magnetic flux creates electric circulation. And then, as usual, he looked at things the other way around. Could changing electric flux, he wondered, create magnetic circulation? The answer promised to solve the capacitor problem.
As current flows into the capacitor, charge builds up, which creates an increasing electric field between the plates. The electric flux through the membrane can be deduced from Gauss's law by imagining a closed surface. All the flux goes through the dome-shaped membrane, and it's equal to the charge on the capacitor plate over epsilon naught. The rate of change of electric flux can be found by differentiating both sides of the equation. It's given simply by the current flowing in the wire. In other words, epsilon naught times the rate of change of electric flux through the dome-shaped membrane is the same as the electric current through the flat membrane.
This was Maxwell's crucial discovery: the precise manner in which changing electric flux can generate a magnetic field as if it were a kind of electric current. In fact, Maxwell himself called this mathematical term the displacement current. In other words, the magnetic circulation around a closed path is given not only by the electric current through it, but also by the rate of change of electric flux through it. This was how James Clerk Maxwell completed the laws of electricity and magnetism. And with these laws, Maxwell could show that electromagnetic waves of every frequency and wavelength would propagate through empty space at the speed of light.
I'm sure that from now on.
Maxwell's discovery, which seemed purely theoretical at the time, would lead to the sights and sounds of the 20th century, radiating through space not only as visible light, but also as radio waves, microwaves, and the entire electromagnetic spectrum. It was a discovery that would lead far beyond the Earth into the deepest reaches of space, where a wave in the intensity of the electric field implies the existence of a changing magnetic flux. That means a wave in the magnetic field. And that's made possible by changing electric flux. And it's made clear only because Maxwell understood that electric and magnetic fields create each other if they move in a wave together at the speed of light. And so it goes, in lockstep through eternity, both fields propagating throughout the universe. And in that light, always at the speed of light, one can finally see the power and the glory of Maxwell's equations. Just as Newton was born the year Galileo died, Maxwell was born in 1831, the year Faraday discovered electromagnetic induction. And he died in 1879, the year of Albert Einstein's birth. What could be more fitting? For between Newton and Einstein, no men in scientific history made a deeper mark. Maxwell went ahead to refine and redefine the fundamental laws of nature, and in the process, to build a bridge to modern physics.
The fact is that Maxwell was endowed with one of the finest minds that the human race produced during the 19th century, and that, combined with his superb Cambridge education, made it possible for him to do absolutely anything he wanted to. I haven't told you about his sense of humor, although once, a long time ago, if you remember, I read to you one of his comic poems about the Atlantic Telegraph Company. Well, I would like to read to you a little bit today from another one of his comic verses. The poem is in this book, which is very old and rare and valuable, and I don't want to handle it too much in class, so I'll just tear out a few pages so that I can read it to you. This is a homework problem. And in the first verse, he sets out the problem. An inextensible heavy chain lies on a smooth horizontal plane. An impulsive force is applied at A, required, the initial motion at K. What he's talking about is there's a chain lying on a table like that, and somebody jerks it at one end, and the question is, how does the other end of the chain begin to move? That is absolutely typical of the kind of extremely difficult and utterly useless problem that Cambridge students have traditionally been trained on. Well, having set out the problem, he then shows us how to solve it in great detail. So I'll tell you what I'd like you to do. I'd like you to go home tonight and work out your homework problems in verse and bring them back with you that way when you come here next time. I'll see you then.
Very good. So I thought this video from the historic and also to visualize and understand, the connection between both electric and magnetic field. You have to remember that is the fact that they are varying, they are oscillating, that does the whole idea here that they can actually move in a vacuum, and the self-generating, of each other, the connection between the two that, that Maxwell showed that on his equation, the last one, is key to understand, how they move in space. Also, another thing was the fact that it has the speed of light. That's another important aspect of his findings. And I want to remind you that all electromagnetic waves move at the speed of light. And that's true for the whole range of magnetic waves, from gamma to to light, different colors, and radio waves. The difference then is the wavelengths that are different. Radio waves are very large wavelengths, and gamma rays are very small wavelengths. And X-rays, gamma rays, they are very, very high energy, and that's why they can penetrate, different materials. And okay, is there any question at this point? Also, I want to point out the importance of collaboration among different scientists. That's extremely important. That each one had its, contribution to help come up and make things clear. So let me move a little forward. So this is, again, the electric field goes, perpendicular with the magnetic field. And one thing to note is that, they go in parallel in terms of the highest point and the lowest point, So is this interdependence between the electric field, changing electromagnetic field, and the magnetic field, the oscillation dependence, is that created this self-propagating wave, right? So they don't need the medium, but they need each other, and they need each other to be oscillating. So that's the key thing to remember. Yeah, I need some drawings. By the way, I already posted this on Canvas. So here you see the electron moving up and down, and the electron has electric field, and the fact that it's moving up and down, it generates a magnetic field that is perpendicular to this motion. Here we have the both equations for the electric field and magnetic field. And magnetic field, you see, depends on V, the motion, the velocity here, so the electric field does not have that component. So a charge that is not moving has an electric field. But once I start, moving up and down, applying some velocity to it, then the magnetic field is generated. And here you see on this diagram here, you see the electric field going outward. This is a positive charge. And as it moves in one direction, it creates the magnetic field, and they are perpendicular. Here I want to emphasize that the electromagnetic field, it is not like this first diagram here. This is just a visualization to demonstrate that both electric and magnetic field have to be present, and they are perpendicular to each other. But the actually, the wave is a 3D, and moves outwards in a 3D fashion. Again, it is this ability of the electric charge and the magnetic field to generate each other. So they, propagate through, co-generation, the electric field and the magnetic fields. So where does the magnetic field comes from? It's basically the moving charge that generates the magnetic field in a form that is oscillating. Why do moving charge create magnetic field? So this is a natural consequence of changing electric field that produces the magnetic field. So I'm kind of repeating this over and over, so so you understand this interdependency between both, and that is what creates the electromagnetic wave. So, and also I want to remind the fact that once the pebble drops on the lake, it goes to the bottom, but that doesn't prevent the wave to keep moving, and that's similar to the electric charge. The electric charge has generated the electromagnetic wave, and then it can travel through vacuum. It doesn't require the electric charge to keep moving along with the and that's kind of I find that difficult to to understand, because when we talk about a conductor that is generating a magnetic field, there is continuous charge being moving there and generates the magnetic field. So you would imagine maybe the electromagnetic field would need to have charge to move, but that's not what happens. So I have this slides that you can go through it and revisit in order to answer the initial question of the presentation today. Here we have the light spectrum, and you see it ranges from radio waves that has very long, wavelengths. Here is 10 to 4 versus a gamma ray, they're very small, 10 to negative 12. And X-ray is right here, a little less than gamma rays. And then visible light is around here. We have the infrared and microwave. So as the wavelength increases, the energy decreases, right? The energy of the wave increases as the wavelength decreases, okay? So the smaller the wavelength, the higher is the energy. And the red has, less energy than, the blue light. The blue light has a smaller wavelength and has more energy there. This is another slide explaining, and here also we can hit the different range of electromagnetic waves that penetrates the atmosphere, and you see here gamma rays and X-rays and ultraviolet does not penetrate the Earth atmosphere, and this is a blessing because otherwise we would be exposed to very energetic radiation, gamma rays and X-rays continuously. Not only when you go to your dentist, but throughout the day. And you can imagine that staying inside the house is not going to help because, those are very energetic radiation and can penetrate, your home. The visible light, thanks God, it goes through the atmosphere so we can see things. Microwave does not. And radio waves, it goes through. And this is also another blessing because otherwise astronauts that are on the moon would not be able to communicate with us. So here is some formulas, that the wave speed is the product of the frequency times the wavelength. So in vacuum, the speed of light, is given by its product. It's 3 times 10 to 8 meters per second. And with this, we see that the wavelength is inverse proportional to the frequency, and we saw that here, right? The wavelength increases, but the frequency decreases. So in radio wave, the frequency is less than the frequency of a gamma ray, right? Frequency is the number of cycles per second. So the cycle, a complete cycle is, you start, go up and come down, and you come to the same position. So that is what a cycle is on a wave. Let's see if I can make a drawing here. So it goes up and down, and that completes one cycle. That's one cycle. So the number of cycles, complete cycles per second, right? The number of cycles per second is the frequency. The wavelength is the distance from this point to that point. Is the length of the whole cycle. That is the wavelength, okay? Now, energy is proportional to the frequency. The higher the frequency, the more energy, and that explains, here gamma rays have higher frequency and higher energy. And it's inverse proportional to the wavelength. So some practical implications of that, so X-rays can be used, in medicinal applications, and because they can, penetrate matter, low frequency waves, we use that in radio waves and lower energy. And here is a slide showing how X-rays are created. Basically, you accelerate an electron. You create a beam of electrons hitting a piece of metal, like copper, for instance. And each electron penetrates the atom and is able to remove, because of its high energy, is able to remove an electron close to the nucleus, so that you need a lot of energy that to happen. And once that electron is removed, there is an empty spot there, and that empty spot, has a tendency to be filled by another electron from the outside shell. And when the electron drops to that position, some energy is being released, a photon of energy is being released, and that's, an X-ray. Okay. So I'm going to stop here, and I'm going to give you some time to complete the second part of the first question that I had, and then you guys do a reflection, and I would appreciate by the end of today's lecture if you could send it to me by email. Is there any question?